This tutorial will describe the setting up of ab initio calculations. In many ways, this setup is similar to semi-empirical computations, and many of the things I've described under semi-empirical are identical here. I'll describe them again, but there may be a better description or a more extensive description under semi-empirical, perhaps, so you might want to look at both descriptions to fill in the details. The first thing you do with an ab initio calculation generally is to choose the basis set. So there are these sort of standard Pople basis sets here, and then there is the ability to have a much larger set of basis sets here. You can pick something, this one for example, and it appears in this list, and you can choose it, or you can choose one of these basis sets. If we choose, say, this basis set, then and put on labels, we'll see that that's the basis set for those three atoms. HyperChem has the possibility of not only having this basis set, but to have an additional basis set. That is, one can have different basis sets on different atoms if one likes. What you do is you just select the atom, go up again, and select a different basis set. Supposing we choose this one this time. Now we're using this basis set on oxygen and this basis set on the hydrogens. In addition to that, there is the possibility of adding extra basis functions up above and beyond these standard basis sets. So if we add an extra function, this can be a particular shell, an uncontracted shell, an S shell, P shell, D shell, and so on. If we choose a shell, an SP shell, an S function, and 3P functions, then we give the exponent, say 1.0 as an example, and say OK, and now we have not only the 631G star basis set on these atoms, but also an extra shell or function. Now I didn't have anything selected, so when I added that, I added it to everything, but I need not. I can go back and select individual atoms and put individual basis functions, set of basis functions on those atoms. Let's go back to a 631G star calculation, for example. No, I guess I gotta take these basis functions away before I get a 631G star. Now I have 631G star on each of the atoms. In addition to the basis functions, there are these other options common with semi-empirical and DFT generally. That is, I have the charge and the multiplicity. For a molecule like water, it would be singlet or triplet. If I am doing singlet, I'm doing RHF. If I want to do triplet, I could do a singlet UHF, but that generally gives the same as the RHF unless there's a specific instability, such as when you have long bond lengths at H2, for example. The UHF is lower in energy than the RHF for singlets. But for triplets, then we would generally use RHF and not use UHF rather. RHF is not really available for triplets. As we've seen, it switched back to singlets when I chose RHF. But I can do UHF triplets, and if I have a molecule like water, I would generally do RHF on the ground state and UHF on an excited triplet state. So in addition to those, we have the convergence controls on the SCF, the convergence limit, smaller number for tighter convergence, the maximum number of iterations we allow, whether or not to use a Poulet algorithm to accelerate the convergence, which we would normally do. And then one has, in ab initio as opposed to semi-empirical, there's an option to compute or not compute the gradient. Because the gradient is slightly expensive, one has that option that you do not have in semi-empirical to not compute the gradient. And same with the MP2, second order molar plusset energy, that can be computed or not computed. It will appear on the status line showing you what the MP2 energy is. the energy doesn't include this, but it tells you what this value is, and you can add the two together to get the total energy with MP2 if you like. So those are those options. The advanced options here are not often used. You can use regular Raffinetti integral format. There's a cutoff for the 2-electron integrals, and there's the number of 2-electron integrals that you actually store in the buffer as you're buffering them in and out off the disk. If you don't want to put integrals on the disk, you can do a direct SCF calculation, which recomputes the integrals on demand, generally slower, but makes possible feasible calculations which have enormous number of integrals that might outgrow your disk space. In addition, you can specify the initial guess to get started. Core Hamiltonian is easy and simple, but not necessarily a very good guess sometimes. You can do have these other options to do a semi-empirical kind of calculation to get the ab initio calculation started as a guess. When you are doing these, you have the option of using 6 Cartesian d orbitals, which is pretty common, or only the 5 spherical harmonics, the 6 reduced to 5. If you use 6, you get, in addition to d character, you get some s character from the 6 d orbitals. So that's basically the options. You choose a basis set, you say OK, you come over here and you decide what kind of calculation you want to do, a vibrational analysis or something, or a simple single point. Push the button, does the calculation, shows you the results, and off you go. If you want to optimize instead, then you push this button, and so on. But the options for semi-empirical, DFT, ab initio are basically the same. Once you've done the setup, you have lots of things you can do, including molecular dynamics, Monte Carlo, transition state, generation of a transition state, and so on and so forth. Having done the calculations, I guess we did a UHF calculation here. You can see the orbitals and so on and so forth. Anyway, that's the basic idea in setting up an ab initio calculation.